Your friend casually sticks out their hand to give you a high five. And you decide this isn't going to be an ordinary high five. And you wind up for the most epic, the hardest high five you've ever given in your life. And then you and your friend are both shaking their hand in pain. But that's kind of weird, right? You hit their hand, so why does your hand hurt? Shouldn't just their hand hurt? Well, unfortunately, this mutually painful experience is due to Newton's third law, which says every action has an equal and opposite reaction. So the harder you hit your friend's hand, the harder his hand hits back. Let's take a look. First, let's review our lesson objectives. We'll introduce Newton's third law, so you understand basically what it is. We'll learn to identify third law pairs. It turns out that in Newton's third law, we always have two forces hanging out, and we call them third law pairs. Lastly, we'll work problems using Newton's third law. Okay. What in the world? How is this guy flying out of the water? Oh, he's strapped to boots, which shoot out jets of water. That's pretty awesome, but I guess it still doesn't answer the question, why do these jets of water force the man into the air? To understand this, we need to think about Newton's third law. Let's actually take a look at this definition, and then we'll come back to this flying aquatic acrobat. Newton's third law, what does it say? For every action, there is an equal and opposite reaction. That's kind of the everyday way of phrasing this, and you may have even heard it before. To put it in more physicsy language, we'll say this. For every force, there is an equal and opposite force. Let me show you what I mean with our good flying friend. Here our friend is in the air and the water is rushing down. And the flyboard is actually exerting a force on the water. That's why the water's pouring down. So water is accelerating downward, and that's what that arrow is representing. If that was the only force present, notice that that would actually pull the whole flyboard and the man with it downwards. And that's actually not what happens. Instead, the man goes up. Well, why does the man go up? Well, it turns out it's because of Newton's third law. This equal and opposite reaction means that the water actually exerts a force on the flyboard. Now, if you were to just casually add up these two arrows, you'd think that the net force was zero. But it's not, because notice that the bottom force is on the water, whereas the top one is on the flyboard. What that means is the water rushes down and the man rushes up. All right, let's think about Newton's third law in this example. For every force, there is an equal and opposite force. Let's focus in on equal. The forces are the same magnitude. So notice those arrows are drawn at the exact same size. So if the force downward on the water is 100 newtons, then the force upward on the flyboard, and hence the man, would be 100 newtons. Now, Newton's third law also tells us that the forces are not just equal, but they are opposite. What does that mean? It actually means two things. First, the forces point in opposite directions. They point in opposite directions. One's pointing down, the other's pointing up. But secondly, and also important, the forces act on opposite objects. What we mean there is that we flip-flopped the flyboard and water and those two Newton laws pairs, so that the top force, as we mentioned, is on the flyboard, whereas the bottom force is on the water. We've actually seen Newton third law's pairs before. For example, we had this force of the anvil on the rope. So the force of the anvil is pulling down due to gravity, and that exerts a force on the rope. Well, the rope doesn't do nothing, it fights back. And it fights back with the Newton's third law pair, which is the force of the rope on the anvil. Typically, we've divided these two into the forces of tension and the forces of gravity. We've seen this same third law pair with our good friend Rock. Hello, Rock, how are you? He's great. He doesn't actually talk. Anyway, the force of the rock on the ground, that's from gravity, and an equal and opposite force pushes back from the ground, the force of the ground on the rock. And we've actually divided these two forces into the normal force and the gravity force. So the normal force is actually another example of a third law pair. Okay, let's go through a few third law pair examples. To do so, we're going to need to understand the formula. For every force, if we have a force of A on B pointing to the right, we have an equal and opposite force pointing to the left. And we're going to flip-flop the subscript, so that's the force of B on A. That's how these third law pairs always work. All right, let's actually put some objects on these B and A things and make them a little more concrete, shall we? All right, for each of these, we're supposed to write each force in the F of A on B format and then state its third law pair. Okay. Number 1 says, a person pushes on a wall with a force of 30 newtons. So the first force we're thinking about there is the force of the person on the wall, and it's 30 newtons. Well, if we want to come up with the third law pair, we're just going to flip-flop that to the force of the wall on the person. Remember, these would be equal in magnitude, so they'd both be 30 newtons, and opposite in direction. This one says that a student weighing 40 pounds sits on a chair. So the first force to think about is the force of the student on what? The chair. Force of the person on the chair. And then the third law pair is going to flip-flop that, so the chair fights back and puts a force on the person. And that's in fact why you don't fall through your chair. Thanks, chairs, for holding us up all this time. A rocket expels hot gases with a force of 10,000 newtons. The force of the rocket on the gas is the first one we notice. But of course, to make that rocket fly forward, we use our Newton's third law pair, which tells us the force of the gas on the rocket. These are both going to be of equal magnitude. So if you accelerate a bunch of hot gases with 10,000 newtons, then that's going to push your rocket forward at 10,000 newtons. So rockets actually fly by Newton's third law. A person in free fall is accelerated by Earth's gravity with a force of 2,000 newtons. All right, this one's for you. Pause the video, see if you can figure out this third law pair. Did you get it? Well, the Earth is accelerating the person, so it's the force of Earth on person is the first force we're describing. The equal and opposite force is going to flip-flop that. And it's going to give us the force of the person on the Earth. That sounds wacky, but actually, this free-falling person exerts a force on the Earth. Of course, 2,000 newtons is a very small force for something as massive as the Earth. So it doesn't do much to the Earth, but it's there. That third law pair is always there. This problem tells us that a boulder at rest has a mass of 1,500 kilograms. What is the magnitude and direction of the normal force exerted on the rocks by the ground? Okay, in this case, we're also given the force is equal to mass times acceleration. That, remember, is Newton's second law. And we're told that gravity is equal to 9.8 meters per second squared. To solve these problems, we're going to go through a series of steps. It's important to draw these on your notes so that you can look at them as we solve the problem. Okay, so first up, we're going to draw a free body diagram. This is just always a good idea when we're given a bunch of forces. Then we're going to list our knowns and unknowns. Again, always a good idea in a quantitative problem involving forces or anything where you are going to be using equations to solve your problem. Then we're going to identify any third law pairs. That's kind of the new step here. That sometimes we have third law pairs which are going to give us that missing piece of information. Then we're going to draw a net force equation, which we've learned to in previous lessons. And lastly, we'll solve for our unknowns. Okay, let's come back to our third law pair problem here about a boulder. And we're going to do our first step first. Shocking, I know. We're going to draw a free body diagram. So we're going to draw a little box to represent a rock. And gravity is going to be pulling down here. So that's the force of gravity down. And then holding that rock up is the normal force. Okay, so now we have kind of a picture of the forces acting on this boulder. Now let's go ahead and list our knowns and unknowns. We're told the mass is 1,500 kilograms. And well, that's it. There's not very much told there, right? Okay, what are we looking for? That's our unknown. We're looking for the normal force. And we want to know its magnitude and eventually its direction. Okay, step 3 is identify any third law pairs. Well, remember, we talked about in our lesson how the normal force and the force of gravity are third law pairs. So here, the gravity is pushing that rock down into the Earth, and then the Earth is pushing back up. So these two are third law pairs. So because they're third law pairs, we can actually go ahead and set them equal to each other. Now, there's really two ways to think about how we can set up this equation. We can say that the force of normal is equal to the force of gravity. And we can know that from Newton's first law because we don't have any motion, right? This boulder is at rest. And if the boulder is at rest, those two forces must be equal and opposite. We could also think about it in terms of Newton's third law because they're Newton third law pairs. Okay, now let's go ahead and start to substitute in some of our knowns. Well, the force of gravity we can solve for with mass times acceleration. So what we're going to do is say that our force normal is equal to mass times acceleration. And we now know our mass, that's 1,500 kilograms, and we know our acceleration due to gravity is 9.8. When we solve for this in our calculator, we'll get 14,700. Now, we need to make sure we round for sig figs, and here we have 2 sig figs in our mass and 2 sig figs in our acceleration. And so we're going to round to 2 digits. So I'll underline the first 2 digits and then realize that that 7 means I'm going to round it up. And so we're going to get that the normal force is equal to 15,000 newtons. Of course, we don't just want to know the magnitude, we want to know the direction as well. It's going to be going upwards, as we know from our free body diagram. So that's up. All right, so that's how we solve for the normal force. Okay, next up, let's go ahead and take a look at one more third law problem. This problem says to accelerate a person upwards, a flyboard expels water with a force of 875 newtons downwards. What acceleration does a 75 kilogram person experience due to this force? And then it tells us to neglect friction. That's nice. One less thing to worry about. Okay. Again, we're always going to start with our free body diagram. So here's our flyboard with our person on it. And what is pushing that person up? Well, we know that there's a thrust force from that water. So we'll call that the force of thrust, TH4 thrust. Meanwhile, there's a force pulling down. And what is that? Well, the person has weight. Due to gravity, there's a force on him, the force of weight. So that's our free body diagram. Those are the only forces acting on the person. Now, notice we haven't drawn yet the force of that water that's being expelled, but that's actually a force from the flyboard on the water. So it doesn't go on our free body diagram. We're just going to think about the forces on the man, which is the force of thrust and the force of his weight. Okay, now let's identify our knowns and unknowns. So what do we know? Well, we know the force of the flyboard on the water. Okay, so we have the force of the flyboard. So we'll put F on W. That's the force of the flyboard on the water, and its magnitude is 875 newtons, and we know it's downwards. Okay, then we know the mass of our person is 75 kilograms. That's helpful. And we want to know the acceleration, so that's our unknown. What is the acceleration? Now we are to the tricky part of our problem, identifying any third law pairs. Well, here our third law pairs are actually going to be the force of thrust and our force from the flyboard on the water. So this guy right here, these guys are third law pairs. Remember that the force downward on the water from the flyboard has an equal and opposite force upwards, and that's what makes the person go up. And so we can actually add that to our list of knowns. We can say that we know the force of thrust. It's equal and opposite, so it's going to be 875 newtons in magnitude, and it's going to be in the upward direction. Okay, so that was a little bit tricky to spot that third law pair. But now we're going to write our net force equation just like we would for a second law problem. We're going to say that our net force is equal to the force of thrust, that's on our man, minus the weight of the man. So that's all the forces we drew on our free body diagram, right? And now what we're going to do is begin to substitute in the proper variables into this expression. The net force we know is going to be mass times acceleration. And there's our A. This is what we're ultimately looking for, right? And we know the force of thrust, so we'll just go ahead and leave that in there. And then the force of weight we know is mass times gravity. Okay, well, if I want to go ahead and solve for A, that acceleration, I'm just going to divide both sides by mass. So I'm going to go over here and I'm going to divide by mass, and I'm going to divide this side by mass. What that's going to do is cancel out the mass over here, and let's do that on white. Boom. And then we're going to get acceleration equals the force of thrust minus the mass of gravity divided by the mass of the man. And by the mass of gravity, I mean the mass of the man times gravity. Now we're all ready to plug in our knowns. The force of thrust, that's 875 newtons, minus the mass of the man is 75, times 9.8, which is the acceleration due to gravity, all divided by the mass of the man, which is again 75. Okay, so what do we get for acceleration? Well, let's see. For acceleration, when we plug all of that into our calculator, we are going to get 1.866 ... and on it goes. Now, we need to round here again for our 2 sig figs because we have 2 sig figs in our mass and 2 sig figs in our acceleration. So we're going to round to the 1 and the 8. That 6 there is going to round that 8 up, and we're going to get 1.9 meters per second squared. Remember, meters per second squared is always our units for acceleration. And there we have it. That man will accelerate upwards at 1.9 meters per second squared. Let's review what we've learned. We've introduced Newton's third law, which told us that for every reaction, there's an equal and opposite reaction. And we've learned to identify these third law pairs in terms of forces that are equal, that is the same magnitude, and opposite. They act on opposite objects and in opposite directions. And lastly, we worked problems using Newton's third law, where we saw that if we knew this third law pair, we could solve for, say, the force of tension when we know the force of gravity. Hey, hey.